Up to number 12 of these Q&A things, asking about differentiating an exponential function if the base is not e. All right, so I've pasted some information from the formula sheet and the syllabus. Okay, but effectively, here's the function, and the question is to differentiate that function. I'm going to assume that a is a constant. Okay, so it's just going to sort of come along for the ride like the 0.06 when I start differentiating. So pause the video and have a go. Okay, if you've had a go, you probably looked at the formula sheet and saw, hey, the formula sheet only tells me how to differentiate if the base is that special number e. Okay, but in the syllabus, it tells me, hey, I also need to recognize and use the inverse relationship of the functions e to the x and natural log x. This is basically that if I have e to the power natural log of x, it's x. And if I have natural log of e to the power x, it's x as well. They're inverse functions. Raising something to the power e and taking the natural log of it is the same as multiplying and dividing, adding and subtracting, squaring and square rooting. They cancel each other out. So we're going to see how this applies to this sort of differentiation. It's questionable whether this is in the syllabus or not, but I can combine those two things together and do this. Okay, so I'm going to start by just making some cosmetic changes to this function. So I'm still writing y because I haven't differentiated yet. Instead of writing 1.335, I'm going to instead write e to the power natural log of 1.355. And all of this will be to the power x minus 27. So you can verify on your calculator, your graphics calculator or scientific calculator, that these two expressions are the same. So now we can use the power of a power index law to multiply these two powers. I'll end up with natural log of 1.355 multiplied by x minus 27 and add this thing on at the end. And just to make it neat, I'm going to give myself a little space because now I'm going to have a go at differentiating this function because I've got e to some power that involves x. I should be able to differentiate that using chain rule. Okay, so the constant that's at the front is just going to come down. When I differentiate e to the power of something, it's e to that power. So I'm just writing this exactly as is. But remember, chain rule says I need to also multiply by the derivative of the function that's normally where x is. So multiply by the derivative of natural log of 1.355 times x minus 27. And then I can go on to differentiate the constant, which I know is big fat 0, and I'm not going to write it there at all. Okay, so all I'm trying to do now is differentiate this function. I'm just going to remember what it looks like if I expanded these brackets. So natural log of 1.355 times x, and then natural log of 1.355 times negative 27. So this is the function I need to differentiate. If I differentiate x with a number out the front, the derivative is just that number. So I'm multiplying by a natural log of 1.355, and then differentiating all this is just a constant. Correction, differentiating a constant is just 0, so I don't need to add anything there. And effectively, I've now differentiated that function. The only thing I'm going to change is that this big expression here also looks like this expression here, which was really just what we started with in our function up here. This part of the function. So using the reverse process, I can rewrite this as just 1.355 to the power x minus 27 multiplied by natural log of 1.355. Okay, so that's what it looks like differentiated, assuming that's just a constant. So effectively, it's similar to differentiating with base e, but we're just out by a factor of natural log of the base. So I need to multiply by that factor. Okay, so good luck doing any sort of similar differentiations that you need to do. I'd recommend not trying to just memorize a whole heap of extra rules that are on the formula sheet. If you can do it from first principles, like we've done in this video, you'll be able to solve more problems and get a deeper understanding of the topics. Okay, good luck.